All right, so we're going to talk about these electric field lines. I'm going to try to stand here in the video and talk to you, okay? So you guys that are in the classroom, you have a booklet. Don't look at the booklet yet, and just sort of stick with me here. We talked about, just like with magnetism, like let's think about this magnet. You've got a magnet, and it's got a north end and a south end. Then we always talk about the magnetic field as emanating or coming out of the north end and looping back around to the south end, right? And we've done that with a compass, and this line wouldn't really be broken. We've done this with a compass, and you've all seen the magnetic field, right? Everybody agree with that? So this is how magnets look. Now it would be really cool if we could break a magnet in half, right? And just have a north end and just have a south end, but we can't do that. If you take a magnet and you break it in half, all you end up with is two smaller magnets, because now this field just loops back to here, and then another field comes out of here and goes there. And you just have two smaller magnets, and this larger field here just disappears. Everybody agree with that? So then this just goes back in there, that goes in there, that one goes in there now. Excuse me, that one comes out of there, that one comes out of there. Because they're coming out of the north and into the south, and now you got a north, south, north, south. And on top of that, what would these two do? Attract each other, right? So that's magnets. So electricity is different. In electricity, we can separate the north and the south. In electricity, you have a positive and a negative, okay? And we know that positive charges, what's basically the basic unit of a positive charge from chemistry? The single basic positive charge is called a proton, right? Everybody agree with that? And the single basic negative charge is called an electron. And the thing is, they have electric fields that emanate from them, just like magnets do. All right? All charges create electric fields around them. So if you have a positive charge, the rules are backwards. We draw electric field lines in the direction that a positive charge would move. So if you had a positive charge near this positive charge, they would repel, right? So we draw electric field lines around a positive charge out. Kind of like the north end of a magnet, right? We draw electric field lines around a negative charge in. So look what happens here. Those two are attracted to each other. Does that make sense? And the field line doesn't stop here. It technically goes forever. So if we have more charge, then we have more field lines. And we end up with two opposites attracting. Does everybody agree with that? And this is stuff that we've talked about before. All right? But if someone's at home watching this video and they've never seen this, now they understand. You draw the lines out from a positive charge into a negative charge. And where the lines come out of the charge, the electric field lines are always, I'm going to zoom in to make a big one here. The electric field lines, say this is a positive, the electric field lines are always 90 degrees to the surface. In other words, they come straight off of the circle. Does that make sense? All right. So let's take a look at this guy right here. I'm going to draw a pretty strong test charge. All right? I'm going to say this is, 0.2 coulombs of charge. All right? And now I'm going to draw the electric field coming out of it, emanating. So the electric field comes straight out of a positive charge And since there's a lot of charge here, I'm going to draw a lot of electric field lines. I just kind of keep coming back and splitting these arrows in half. That's how I'm trying to make it like look neat. Everybody feeling that? Now we can talk about the intensity of the electric field. We can talk about the intensity of the electric field here, okay? What do I mean? If you are a negative charge and you're way out here, you are less influenced by this than if you were close. Look here close to the circle. The lines are very, very dense. Look how close the lines are together. If I move my finger this far, I can cross 5 lines. If I go way out here and I move my finger that far, I only cross 1 line. Does that make sense? So we realize that the further we get away from a test charge, the further we get away from a charged object, the less intense the electromagnetic field is. The intensity of the electromagnetic field is called E. So write that down real quick, please. The intensity of the electromagnetic field is called E. And if we look here at our tables, we can see there are several formulas that include E. Look at these formulas right here. E is equal to F per Q, right? And E is equal to KQ over R squared. And E is equal to V over D. Now, the one I'm thinking about right now is E is equal to K times Q over R squared. Now these are all equal to each other, right? But the first thing we're going to talk about is this formula right here. E is equal to KQ over R squared. I'm going to make a mark on this so I can come back to it. All right. So if we come out here and we're going to talk about E, I'll talk about E at this point right here. Dink. E is the electric field on a test charge. On a test charge. So what it means is, if this is, Ethan, if this is a proton or an electron, that's our test charge. If this is a proton or an electron, how intense would the field be on this thing? Okay? E is equal to KQ over R squared, right? Right? So if we look at our formula, E is equal to KQ over R squared. So this is the formula we will use. If this is an electron, which way would it move? Yeah, if it's an electron, it's going to be attracted. If it's a proton, it's going to move away. But the electric field intensity here, electric field intensity for each of these will be the same. So what is the electric field intensity right here, this far from a charge? All right? Well, let's see how far away it is. I'm going to say this is half a meter. Okay? So E equals KQ over R squared. E is equal to KQ over R squared. So what is the electric field intensity half a meter from a 0.2 Coulomb charge. That is the question. What is the electric field intensity 0.5 meters away from a 0.2 Coulomb charge? That's the question. That's very sloppily written. So if we look right here, we can do some simple math. E is equal to, this is K is 9 times 10 to the 9th times the 0.2 Coulomb charge, 0.2 Coulomb, and the distance we're away is a half a meter, 0.5 squared. (7.2) times 10 to the 9th. Now you would say, Mr. Perkins, I know the answer now is 7.2 times 10 to the 9th, but I don't know what those units are. 7.2 times 10 to the 9th. What units are they? The units are coulombs per meter squared. All right? Now let's look at the next formula. What's that, dude?
We don't happen to have any more of these.
No, I don't really use like a lot of those. Hang on, let me pause. So when we're talking about these units, the units seem like they're garbage. It's like, well, coulombs per meter squared. What does that mean? Well, that's literally what it means. That's how much charge it would represent in a square meter of area. So the last thing I would say is, if you look at the other formula, doesn't it also say that E is equal to F per Q? Right? So check this out. E is equal to F per Q. Now we can take this number and realize that this is Coulombs Law. Because right now we can say this number is equal to F per Q. What does that mean? Where's my board? Here we go. If we wanted to, we could now say, oh, okay, if the electric field intensity on a test charge right here is equal to 7.2 times 10 to the 9th coulombs per meter squared, we can also look at the other formula that is now E is equal to F per Q. All right, so if this is, didn't we just say this was an electron? What is the charge of an electron? Negative 1.6 times 10 to the 19th. Everybody agree with that? Times 10 to the negative 19th. Right? The electric field intensity is 7.2 times 10 to the 9th. So now if we said this times this, that will tell us the net force on an electron that far away from there. Okay? So if we did that, let's do it. These two numbers multiply by each other. 7.2 times 10 to the 9th times 1.6 EE 19 negative equals 1.15 times 10 to the negative 9. (1.15) times 10 to the negative 9. So get here. (1.15) times 10 to the negative 9 newtons. So that's literally how much Newton force, how hard it will be pushing on one electron. Now, since this year we're squeezed for time, and this is the last day. The only thing I will ask you to understand about this is that E is equal to KQ over R squared. So if you know how strong a charge is and how far away from that charge you are, you know the electric field intensity. In a normal year, then I would ask you, oh, okay, how hard would it push on an electron at that point? Does that make sense? We've already done Coulombs Law, correct? Isn't this Coulombs Law? Coulombs Law is the force in newtons is equal to K times charge 1 times charge 2 over R squared. Right? This is what we just did. We just did the formula in two different halves. I took one of the Q's and moved it over. Does that make sense? So it's really just Coulomb's Law. All right. So that's electric fields around charged objects. Okay? Really quickly, I want to show you something that's important. What if you had a piece of metal, piece of ceramic, and stuff like this, and inside of that piece of ceramic, I want you to watch closely, because you know I was talking about dirt bikes. And then we got like a coil right here, really, really wrapped up coil, and you can't see it because it's hidden under a piece of ceramic. Then that coil is hooked up to a wire, touches a piece of metal, and then that piece of metal's got a little hex nut on it like this. And then the piece of metal with the wire hooked up to it goes down, and now it's got threads. And we take this piece of metal and attach it here. We take another wire, and we attach it here to the end of a little piece of metal right there. Here's the other wire. What is this thing? Anyone tell me what this weird picture is I drew? It's part of a motor. It's very important. When you give this enough electricity, the coil pack here, the coil, creates enough of a voltage that a spark jumps from this place, from the positive to the negative, just jumps across. What is this piece? That's a spark plug. That's how a spark plug works. We literally create enough voltage to jump this gap, and it makes a spark. It just jumps right across. That's what a spark plug is, all right? So what is a spark plug doing? How does it work? This is the last thing that you need to know. We're going to talk about parallel plates. Parallel plates in fields, electric fields. All right? All right. We're inside of a battery here. We have one plate. We'll say that this plate right here, I love it. We'll say that this plate right here is the positively charged plate. And that this plate down here is the negatively charged plate. Oh, that's not very parallel, is it? This plate down here is the negatively charged plate. All right? Now these will be stacked up in a battery, and in between them, you could literally have air. In a battery, we have like a chemical in between them to facilitate the movement of electrons, right? Well, let's say these are just two chunks of metal that we've hooked up to a 12-volt battery. Okay, that just makes it easier to think about. The positive piece of metal is hooked up to that one, and the negative piece of metal is hooked up to that one. Everybody agree with that? Okay. Now, just like a spark plug, if you held these things close enough together, electrons would just jump from this plate to that one. Do you agree with that? Right? So let's draw the electric field between two parallel plates. How do you draw the electric field in the direction a blank would move? A positive charge would move. That's exactly right. So if you were a positive charge and you were in this field, which way would you be moving? Towards the negative or towards the positive? Towards the negative. So if you're drawing an electric field between two parallel plates, you draw perfectly straight, evenly spaced lines because that's the direction of the electric field. Okay? So now we're inside a battery, in the plates of a battery. And as long as you're not near the edge, you have a perfect, evenly distributed electric field. You with me? Now, the first thing I could tell you about this is the electric field intensity here between these two plates. The electric field intensity is equal to volts per meter. So the strength of this electric field in here, if you're in the middle and not near the edge, the electric field intensity is equal to how many volts this battery is and how close these things are together. Do you not agree that the closer these things are together, the more intense the electric field and the more likely it is for a spark to happen, right? So this is kind of common sense. Do you agree with that? This is almost just a common sense equation. All right? But here's something you need to know. Batteries can do work. Batteries can do work for us. A volt is a joule per coulomb. Okay? So ready? A volt is a joule per coulomb. So a 1 volt battery can do 1 joule of work if it moves 1 coulomb of charge. Ethan, you need to write this down and draw this. So a 1 volt battery can do 1 joule of work for you if 1 coulomb of charge, 1 coulombs of electrons, go across the electric field. So how much work could a 12 volt battery do with 1 coulomb of charge? 12 joules of work. If you had a 12 volt battery and 1 coulomb of charge, 1 pile of electrons, it could do 12 joules of work. So higher voltage batteries can do more work with the same amount of electrons. Does that make sense? Because they can move those electrons with more force. And work is equal to force times distance. See how we're tying like real world practical hands-on physics to what's happening with electrons? Okay? So since this year, this is the last day, I'm going to leave that at that. A higher voltage battery, 1 volt is equal to 1 joule per coulomb. Done. All right? How do we, I'm going to talk to you about the important parts of batteries now. How is energy stored? How do batteries have potential energy?
Build up of electrons.
What's that?
Build up of electrons.
Yeah, this battery has potential energy because we have one plate that has excess electrons and another plate that has too few electrons. Or we have one plate that can easily shed electrons and another plate that would like to gain electrons, however you want to think about it. All right? So that is how energy is stored in a battery. Now, the more electrons we have down here, the more energy is stored. Do you agree with that? So if you have more electrons down here, then you just change the voltage of the battery. Does that make sense? So if we had bigger plates and to store more electrons and higher voltage, then you have more potential energy. That's why your car has a big battery with big plates in it. Does this make sense? Okay, so let's talk about some simple stuff that you have in your work packet in front of you. Hey, what would happen right here, Katie, if I put a proton right there? What would it do? It would move down. Does everybody agree with that? John, what's dumb about me drawing a proton here? Why is it dumb for me to draw a proton here in this battery? Anybody Anybody?
Why would protons be there?
Exactly. What should I draw here? An electron, yeah. Dude, just dumb to talk about protons. We're doing electricity. Like, let's talk about electrons. Now, I got an electron right here. I'm going to draw it in red. I've got 3 electrons drawn here. Which one of these electrons has the most potential energy? Ryan. Yeah, this one's got longer left to move. This one has the most potential energy. This one has the least potential energy because it's only going to move that far. Does that make sense? All right, next thing that's important. All 3 of these electrons, if we took a picture of them, are moving at the same speed. And all 3 of these electrons, right, are experiencing the same electromagnetic field intensity. They're experiencing the same force. Now this may seem weird to you. You may be like, Mr. Perkins, look how close that electron is to that proton. According to Coulombs Law, the closer you are, the more attraction you have. That one's experiencing more force on it. And I would say, no, because look how far it is from this negative. This negative is barely pushing it. Look at this one. This one's being equally pulled and equally pushed. And this one's being pushed really hard and pulled really weakly. So they're all 3 experiencing the same electric field intensity and the same force. So they're all moving at the same velocity, and that velocity doesn't change as they go through there. Yes? Yeah, buddy. As long as your phone stays in here. So, does that make sense? That's a basic concept. So this battery can store potential energy by holding electrons in a place where as soon as we let them, they will go somewhere. It's no different than putting a vase on a high shelf. Do you agree with that? Right? So there's math problems we can do in here. Like, if this was an electron, we could do a math problem about the electric field intensity on it. But this semester, with 20 minutes left in class, I'm not going to talk about it. I will say this. What would happen? I've got a magnet in my pocket, and it kept sticking to the board. I was like, what's happening? I will say this. What if I had an electron, and I tried to shoot it right through here? What would that electron do? It would what? Yeah, it would swoop. It would go like this. It would go. If it was an electron. Does that make sense? So, depending on the voltage of the plates, this electron would go so far. Right? If we're shooting the electron with the same amount of energy, and the plates were different, the electron would curve and hit at a different place. Does that make sense? Or if we had a consistent voltage, and we moved the electron with different amounts of energy, with different amperage, right? With different force on the electron, then it would go certain distances. And that's the basis of an old television and how it works. And I know that's not enough. I would need to talk to you for 5 more minutes. But that's the basic technology.